Hi, everyone. Welcome back. In this mini lecture, we're going to talk about some general properties of electrons in periodic potentials. So let's again remember how we got here in the first place. Remember, we started this class with the discussion of the Drude model, which considers electrons as classical particles that collide with ions. We assume they're free and independent, and they reach equilibrium by this process of collisions. Remember, again, in the Sommerfeld model, we relaxed the assumption that the electrons must be classical particles. We started to take into account their quantum mechanical properties. Now we've embarked on a journey of allowing the electrons to interact with the potential of the ions, not just during collisions, but all the time. And last time we talked about Bloch's theorem, which says that the single particle solutions to the Schrodinger equation with a periodic potential have the following form. They're characterized by two quantum numbers, n and k, and the wave functions look like plane waves times functions which depend on n and k and have the periodicity of the lattice itself. They have the periodicity of the periodic potential that appears in the Schrodinger equation. Now, this will be one of the main developments of the course, and we're going to unpack some of the ramifications of Bloch's theorem in the coming lectures. This will lead us to band structure and associated topics. Today's mini lecture and the next one will focus on some more general properties of electrons in periodic potentials. So let's remember, in the last set of mini lectures, we derived Bloch's theorem in a few different ways. The first focused on some formal quantum mechanical arguments relying on the properties of translation operators. Our second derivation involved a Fourier expansion of the Schrodinger equation. We can do this because the potential is periodic, and by applying periodic boundary conditions, we can feel free to do that for our wave functions as well. These periodic boundary conditions, as we saw, also quantized the allowed values of the wave vector k. And remember that we computed the volume per allowed point in k space within the framework of Bloch wave functions, just as we did for free electrons in the Sommerfeld model. And we found that the total number of allowed wave vectors in the first Bloch zone in the primitive cell of the reciprocal lattice is equal to the number of sites in the lattice altogether. So in some sense, the first Bloch zone contains all of the information one needs to know about the entire lattice. So that's an important point to remember, which will come back again and again. So let me write that down as 0.0. Again, the first Brillouin zone, the primitive cell of the reciprocal lattice, contains a number of allowed wave vectors, k, equal to the total number of sites in the crystal. So this mini lecture will concentrate on some general features, some comments about electrons in periodic potentials. So the first comment or question we can ask is, what is the significance of this wave vector k? remember, in the Sommerfeld theory, we said that that wave vector k is essentially equal to the momentum of the electron. We said that p is equal to h bar k. In this case, though, in the case of Bloch electrons, k is clearly not the momentum. So you can see this on a formal level by noting that the Hamiltonian no longer has translational invariance. So eigenstates of the Hamiltonian are not eigenstates of the momentum operator in this case, right? The Hamiltonian is still time invariant, but it's no longer spatially invariant as it was in the case of free electrons. That was the fundamental feature that allowed us to construct simultaneous eigenfunctions of the energy and momentum operators. Now, when we talk about a potential that's not spatially translationally invariant, we can no longer construct simultaneous eigenfunctions. On a different level, you can see that if I apply the momentum operator on a function of the Bloch form, we can see that a Bloch wave function is not an eigenfunction of the momentum operator. So the momentum operator is h bar over I times the gradient. If we act this upon a Bloch wave function, we get h bar over I times the gradient acting on e to the I k dot r u and k r. This is equal to h bar k times psi at r. But there's an additional piece which comes from the gradient acting on u. So you can see that this wave function psi is not an eigenfunction of the momentum operator. Thus, k cannot be, which is one of the quantum numbers, cannot be the momentum itself. We'll see in the coming lectures, though, that h bar k is still related to the momentum, though it's not exactly the same thing. It is called, h bar k is called the crystal momentum. So perhaps somewhat confusing at this stage, I know. The thing that you should take away from this is that k is no longer the momentum of the electrons, but it is still related to the momentum. And it's sort of close enough to the momentum that we call it something similar. We call it the crystal momentum. And as I say, we'll talk about this more and more in the coming lectures. Okay. So the next point to think about and understand carefully is that we can always choose this wave vector k to lie in the first Brillouin zone. We can always choose this wave vector, this quantum number k, to lie in the first Brillouin zone. And on a fundamental level, that's because, remember, the first Brillouin zone essentially contains all the information about the crystal. It has a number of allowed wave vectors equal to the number of atoms, the number of sites in the crystal. More formally, you can see this in the following way. Suppose I have some Bloch wave function, psi nk at r, which is e to the I k dot r times u of r. U, again, has the periodicity of the lattice. Here's the plane wave. Now, let's suppose we pick a different wave vector. Let's suppose we displace it by a vector that's in the reciprocal lattice. So psi of little k plus big K is a new Bloch wave function. It is not in the first Brillouin zone because we've displaced it by a reciprocal lattice vector. It's essentially closer to another reciprocal lattice point than the origin. The Bloch form for this is e to the I k dot r times e to the I big K dot r times u, the different function now, which depends, or which has the periodicity of the lattice. But you see that I can write a different function, u prime, which is equal to e to the I big K dot r times u itself of little k plus big K of r. So this function has the periodicity of the lattice. You can imagine that it's constructed as a Fourier expansion in reciprocal lattice vectors. But if I simply multiply this function, which has the periodicity of the lattice, by this plane wave, which also has the periodicity of the lattice, the resulting function still has the periodicity of the lattice. So even though I picked an initial wave vector that was outside the first Brillouin zone, I can pick a new function u such that this function has the Bloch form with this wave vector little k in the first Brillouin zone. Again, this is because essentially the first Brillouin zone contains all of the information about the lattice. The information in higher Brillouin zones, in zones away from the origin, is essentially a duplicate of the information in the first Brillouin zone. Again, this is something we'll come back to again later on in this class. Okay, so what have we talked about so far? The distinct values of k lie in the first Brillouin zone. We can always choose k to lie in the first Brillouin zone. You give me any wave vector k, I'll show you an equivalent Bloch wave function with k in the first Brillouin zone. K, we've discussed, is not exactly the momentum, but it is related to the momentum. It's called the crystal momentum. The next observation we can make is there are actually infinitely many solutions to the Schrodinger equation for a given value of k. So you can see this in the following way. Let's again assume we have a wave function. I'm going to suppress the quantum numbers n and k here, which is of the Bloch form. If we demand that this satisfies the Schrodinger equation, we can say that H acting on U is equal to H bar squared over 2m, 1 over I times del plus K squared plus the potential U acting on little u of R is equal to the eigenvalue E times U of R. So if you like, I've simply substituted this wave function into the Schrodinger equation. I've canceled out the plane wave from both sides. So what I'm left with then is an equation that U must satisfy. And we can now, because you see that K appears in the Hamiltonian as a result of this plane wave, let's imagine thinking about it as a parameter of the Hamiltonian and also of the function u. So this equation, this Schrodinger equation, is really now an eigenvector equation for the function u. Okay. this is it's an eigenvalue problem. We can also observe that U is periodic. In the Bravais lattice. So this is an eigenvalue problem in a fixed volume. If you like, you can think back to the particle in a box. That's an eigenvalue problem in a fixed volume. In that case, there's an infinite set of eigenvalues and eigenfunctions. So it is in this case too. In general, we'll expect an infinite set of eigenvalues, E for a fixed value of K, with corresponding eigenfunctions U with parameter K. We use the index N to specify these different eigenfunctions and eigenvalues for a fixed value of K. Okay? Good. Let's make another observation. So we've seen that it's possible to specify all the levels, all of the resulting levels associated with the solutions to the Schrodinger equation by restricting K to the first Brillouin zone. We could decide to let K range over the entire reciprocal lattice, over all values possible in the entire reciprocal lattice. But then we would have to agree that the set of wave functions and levels for two values of K differing by reciprocal lattice vectors should be the same. So we could let K exist outside the first Brillouin zone in addition to inside the first Brillouin zone. But as we've seen, I can always pick a K to lie in the first Brillouin zone. So if we let K exist outside the first Brillouin zone, we should agree that psi of K, little k plus big K, where again, big K is some reciprocal lattice vector, should equal psi of n and little k of R. In other words, the wave functions and also the energies associated with wave vectors that differ by reciprocal lattice vectors should be the same. And this again is because the only distinct wave vectors really lie within the first Brillouin zone, and there's no R dependence of the energy here. Okay, so what this means is that if we want to think about allowing K to exist outside the first Brillouin zone, E of n and k is a periodic function in little k. And this periodic function is called a band. So again, the logic is the following. If we decide to allow K to exist outside the first Brillouin zone, we need to agree that wave functions and also eigenvalues associated with two values of k that differ by reciprocal lattice vector should be the same. What this means is that E is a periodic function of the wave vector k. It has the periodicity of the reciprocal lattice. Because it's periodic, therefore it has a maximum and a minimum. It is therefore called a band. This is the origin of the term energy band. And it's something we'll continue to discuss in the coming days and mini lectures. So at this point, if this is confusing to you, that's probably good. This is rather challenging to understand. One thing I find helpful is to consider the behavior of free electrons in 1D. So you know that the wave function for a free electron in one dimension, psi of x, is proportional to e to the I kx. Okay, and the allowed values of k depend on the size of the sample that we're considering. Let's call this psi k of x. This wave function clearly has the Bloch form. It's a plane wave times a function, which is just unity, that obviously has the periodicity of the lattice. We'll say if the lattice itself, remember this is a fictitious lattice here, has lattice constant A. We can associate a primitive vector, which is not really a vector in this case, it's a primitive distance with A, that lattice constant. We can say that the reciprocal lattice primitive distance is 2 pi over A. Remember that we construct the first Brillouin zone essentially by bisecting the line between the origin and the nearest reciprocal lattice points. So the first Brillouin zone has boundaries plus minus A, or plus minus pi over A rather. Good. So we can say that if k, now this wave number associated with a plane wave, is outside the first Brillouin zone, we can say that k is equal to k prime plus n big K, where big K is equal to pi over A, and n is an integer. And k exists between minus pi over A and pi over A. So let me actually switch the notation here to say that given some wave vector k outside the first Brillouin zone, we can define a new one, k prime, which is in the first Brillouin zone here. And we've shifted k prime to be in the first Brillouin zone by adding to k an integer multiple of this primitive distance, which itself is a distance that belongs to the reciprocal lattice. We can bring k prime back to the first Brillouin zone. Okay. So we can say that psi k of x is equal to e to the I k prime minus n k of x. K prime is in the first Brillouin zone. Little k is not. So this is e to the I k prime x, e to the minus I n k x. This is equal to e to the I k prime x times u, a function u which depends on the parameter n of the position variable x. So we'll call this psi n k prime of x. So this is another Bloch wave function. This is a perfectly valid Bloch wave function. You see I've chosen the wave vector now k prime to lie in the first Brillouin zone. Here's a function which is periodic in the lattice itself. It's a slightly different function than what we picked before. Okay, so the point of this is that we can always choose the wave vector k prime to lie in the first Brillouin zone. And how we do that involves using this extra quantum number n here. So let's look at the energies. So E of k is h bar squared k squared over 2m. That's the bare energy, where here k can range over the entire reciprocal lattice. But I can also write down E n of k prime as h bar squared over 2m k prime minus n times big K, where now k prime is restricted to lie in the first Brillouin zone. Okay, so again, you see that if I decide to restrict the wave vector to lie in the first Brillouin zone, I'm perfectly free to do that. The way that we can keep the bookkeeping correct is by introducing a new quantum number n, which essentially describes how far away was that original wave vector from the first Brillouin zones. Okay, so we can now write down, or we can draw energy diagrams for these different states of affairs. So in the case where we allow the wave vector to exist everywhere in the reciprocal lattice, or at all allowed values in the reciprocal lattice, we simply have the free electron parabola. But if we decide to restrict k to lie in the first Brillouin zone, so here are the boundaries, plus minus pi over a. Now we would draw a scenario that looks like this, where this is the n equals 0 branch. This would be the n equals plus 1 branch. And this would be the n equals minus 1 branch. So if you go back to the expression we wrote down before, En of k prime is h bar squared over 2m k prime minus n big K, which is pi over a squared. I may have forgotten the squared on the previous screen. Here's the squared here, where again k prime can range between minus pi over a and pi over a. So these are equivalent representations. Here, in this case, on the right-hand side of the screen, we've restricted k to lie in the first Brillouin zone. That's a good idea because really the only physically distinct values of k lie within the first Brillouin zone, as we saw earlier. You give me any value of k, I'll give you an equivalent value of k that lives in the first Brillouin zone. So let's make one final comment about the velocity of Bloch electrons. Remember, for waves, we typically define a group velocity. As d omega dk. In the case of free electrons, it was straightforward for us to write down the velocity h bar k over m. For Bloch wave functions, perhaps surprisingly, it is still true that the velocity of an electron with wave vector k in band n is equal to 1 over h bar times gradient with respect to k of the energy of the nth band at wave vector k. So this is very much analogous to d omega dk, right? If you imagine that the energy E is h bar omega, you see that this function is very much the three-dimensional analog of this. I won't prove this now to you. We'll sketch out an argument later on in the course. For now, perhaps it's enough to realize that although it's surprising, this form of the velocity is indeed still true, okay? This has some surprising implications if you think about it. What this means is that there are eigenstates of the Schrodinger equation with the periodic potential that have, in general, a non-vanishing velocity, okay? This is surprising because there's a periodic potential in place. So one might naively expect that this potential should disrupt the motion of electrons, but it need not. There are electrons that have a non-vanishing velocity. There are Bloch electrons that have a non-vanishing velocity in spite of the presence of the periodic potential. So this is one indication that even this now somewhat advanced discussion of electrons and periodic potentials still cannot account for dissipation. So this is, again, a somewhat surprising fact if you think about it. It again is in, or it also rather is in direct conflict with our intuition from the Drude model. When we were thinking about the Drude model, we thought that it must be the lattice of ions that causes collisions associated with electrons. That clearly cannot be the case. The periodic potential associated with the ions, as long as it's periodic, cannot cause collisions, it cannot cause dissipation. So this is now the first indication that even the highly advanced and somewhat complicated band theory still doesn't explain everything about electrons in metals. The resolution is that we need to consider deviations from perfect periodicity in the lattice. We need to think about things like defects or vibrations in the lattice. We'll come to these topics later on in the course.